Start recording. Okay, so today's topic, system responses. Simply, what we are talking about, what happens to a signal, digital signal when it goes through a system, and what is the output. So we are just focusing basically for that one. So what kind of responses there are. From yesterday we know that, okay, if we have a linear time invariant system, the system is defined by the system coefficients B and A, which are vectors. Let's mark them as vectors. Yeah, so system coefficients actually define totally the behavior of the system. Now we do some analysis, what kind of responses actually are important. Okay, first, which is the most important property, is basically the impulse response. So it answers the question that what is the output for unit impulse input. Okay, so for example, for 4-point running average filter, it's the data which is defined by those filter coefficients. Good morning. You have been running. Okay. So 4-point average filter, and we have delta in. What comes out? Okay, that's the delta input. What comes out? For example, that 4-point running. 4-point running average filter. It's something like, this. The volume value is 1/4. Okay. So, yeah, some graphs. I even have those here. Based on the impulse response, the systems are divided in two. One is the finite impulse response system. Basically, the definition that the impulse response returns to the initial state at some time step. For example, this 4-point running average filter is an FIR filter because after the third delay element, or after time 3, it returns back to initial state, which is 0. Okay, so 0 minus 1, 1, 2. So actually, there is a easy test for if the system is IIR, then basically impulse response after the highest order delay will be non-zero. Okay, feedback actually is a required element to get an IIR system, but if a system has feedback, it does not guarantee it's the infinite impulse response. Like the 4-point running average, you can calculate it with feedback, but it's still, by testing, you can test that it's still infinite impulse. It's still finite impulse response system. Okay. Most of the natural systems are infinite impulse response systems. So think of, for example, a RC low pass filter or high pass filter. It has this exponential decay for the step response, so it basically never reaches the initial state. So if you sample that one perfectly, then it's infinite impulse response system. Just like most of the real-life systems. Not all, but most. Quantum mechanics, actually, these phenomena can be finite impulse response systems. Okay. Transfer function and impulse response. There's a nice relationship. Actually, transfer function is the same as the Z transform of the impulse response. So if you put impulse in, you get the impulse response out, and from impulse response, you can easily get the transfer function just by making the Z transform of impulse response. If the system is, type is finite impulse response system, then it works, but of course on real life you don't have infinite time to wait. So this is more or less like mathematical formula to do it for IIR systems. Or the system recognition, how to recognize that your model, what you are basically trying out, actually fits with the system impulse response. Well, you actually optimize this system coefficient so that you will get that one using that formula. But that's out of the scope of this course. Advanced topics. Although in MATLAB it's quite simple to make there's toolbox for system identification. So it's quite straightforward to make the test for the system and let the MATLAB to decide what is the good model for it. It's usually brings a model as an IIR system. Okay. Zeros and poles. Yesterday we talked about these special points. IIR system actually, well, FIR systems have all poles at origin or cancelled by a co-locating zero. Just like those two top pictures here. This is the 4-point running average filter, the feed-forward kind of type, straightforward calculation. The left-hand side is with the zero pole plot for the system with feedback, and actually there is the pole locating on at real axis at point 1, but there's also co-locating 0, so it cancels that out. It basically comes directly from the well, yesterday's material. There's the formula showing that, okay, we added a special point so that we could actually make this faster to calculate. IIR systems, they all have at least one pole off the origin. So somewhere between 0 and 1, the radius. That actually then tells that, okay, this is IIR system. Definitely IIR. Okay. Yeah, another responses, time-based responses like step response. So system output for unit step input. Well, yeah. And the definition again, you put a unit step function in, and what comes out is this step response. Nothing more into it. So that's quite handy actually when you are having a function generator and some electronic system, you run the rectangular wave from the function generator and look the output on the oscilloscope screen. So basically, that one then you are looking at the step response practically. The same thing as with the analog electronics. I think you have done some of the exercises on the first year and trying to fit the Laplace transform and figuring out the parameters, the real values for the components. Oh boy. Okay, but yes. So this is step response is used mostly just to check how the system would look like in real life, meaning analog system, as an analog system. Okay. 4-point running average filter. Well, with this input, you will get kind of ramping up signal on the edge, nothing more. Not really, say, exciting signal. Okay. Then we have this arbitrary signal response, which means actually that we are filtering a signal. So for any signal which goes in, you can calculate the output using the difference equation, or actually, even better, you would do it by whatever your block diagram looks like. In MATLAB or Octave, this arbitrary signal response is basically calculated by command filter, where you have those filter coefficients, B and A as the parameters, and the third parameter is the input data. MATLAB actually has pretty efficient the filtering tools there. But the difference equation is one way of calculating it, not the most efficient way. Okay, yeah, that's why difference equation as it is does not give you the answer how to calculate it. Just a reminder from yesterday. System transfer function. Good morning. Hey, we have the full pack here. Half dozen. Is it dirty half dozen or? So system transfer function. If you evaluate system transfer function on the unit circle, complex Z-plane unit circle, you will get actually the frequency response, complex frequency response. Okay. You should have had the frequency response for analog systems already, an S-plane, 2 years ago, something like that. It's usually first year classes that you will actively try to forget. Okay, but anyways, let me show you. So if you have an analog system and you have the analog system, the transfer function H of S, and then you have the complex S-plane, you have a couple of poles. Here maybe you may actually have some zeros locating close to the real axis. Here our signal is actually on the imaginary axis. So you are evaluating H of S at S equals J omega. That gives you the amplitude response, or the frequency response, complex frequency response. Okay, that's in analog systems. In digital world, we have, instead of this S-plane, we have Z-plane, where the zeros and poles locate, for example, like that. 2 zeros, 2 poles. Here, our signal is actually, corresponding signal is on the unit circle. So in here, our frequency response is something like that. E to j omega, the transfer function at e to j omega, where omega is actually that corresponding angle, which is simply 2 pi times physical frequency divided by sampling rate. Right. So it's a direct mapping. So this angle, well, in this analog systems, our frequency actually is on j-axis. Here we have the signal with unity frequency, unity amplitude is on this axis, and in for the digital systems, actually the frequencies are on unit circle, and the angle gives the physical frequency. Okay, makes kind of sense, maybe. Okay. So it's evaluated on the unit circle, and if you still remember something from yesterday, you should remember also that there are some, you can actually show the transfer function as either as the this kind of transfer function, rational polynomial of those sums, or you can also show it as the product of the route g to e to j omega minus 0 point divided by product of e to j omega minus pk. So yes, now you can practically calculate the frequency response. You just need to vary the omega from 0 to pi. That gives you the frequency response. No need to evaluate the negative side, since it's, as you can see, it's always symmetric. Same way as in analog system, you have the positive and negative imaginary axis. They are basically, it's a mirror image. Same thing here. It's always mirror image against the real axis. Okay. This complex number actually can be then separated into magnitude or amplitude response. So amplitude response is simply the absolute value of this, which is basically absolute value of, well, that's the normal basic, but well, the same thing. It is still the same thing, although the mathematicians don't like that. But what can I do? Haha, they are not here. Neither they are on the real life working in biomethod. Sorry. Actually, I do know some brilliant mathematicians which are doing really good job in industry, but they are rare. Most mathematicians are more about the very theoretical kind of things that doesn't touch the reality. All right, and then we have this kind of stuff here. So absolute value, or well, let's mark this one normal. Complex number minus complex number, difference of two complex numbers and the norm of it. Graphically, that this one here, let me mark it with blue color. Graphically, this here is distance from this e to j omega point to here. And that number is multiplied by this distance. So that distance is e to j omega minus z1. This is e to j omega minus z2. So those are distances to the 0 points. Same way, the on denominator, here this norm, we have distance from this point to pole 1 and distance of this point to pole 2. And the product of those. Okay. But you can say actually from this diagram already, or graph already, if you have a situation when the this actual frequency goes at the same point as the 0 point, you have 0 response out from the system. So the amplitude response goes to 0 at that point. They are same. Distance is 0. Okay. Let's sketch this a little bit. So this is the amplitude response graph where we had the okay, that is the angle of the first 0 point. And we know that frequency response goes to 0 on that point. Yeah, and then must go up on both sides. The same way, actually, when the angle approaches the same angle where the pole is, you get the minimum distance there, which means that you get minimum of the denominator, meaning maximum point for the amplitude response. So if that was omega 2 here, omega 2, that's the local maximum. And nothing interesting is happening in between, meaning that we can actually guesstimate what the frequency response could look like. Something like that. Based on those special points, zeros and poles on the unit circle. It gives you a suggestion of what this frequency response could look like. So frequency response goes to 0 when the frequency is the same as the 0 on unit circle, and then it has a local maxima when frequency is close to the angles of the where the poles are. Okay. Phase response. Well, yeah, I will come back to the phase response later. There is an example of 3-point running average filter. No, sorry, 4-point running average filter. Remember the zeros and poles for 4-point running average filter were basically 4-point running average filter has zeros on those points and poles here. Or actually, if we have this kind of situation with the feedback, well, those will cancel out before you do the calculation here. So they are the same place, meaning that they will be subtracted from both numerator and denominator. Okay, so we have at angles of 0.5 pi and 1 pi. You have special points just like here. There's a normalized frequency 1 times pi, and the another one is 0.5 times pi. Okay. Yeah, and normalized frequency is nothing more than 2 pi physical frequency divided by sampling rate. It's a linear mapping. Linear mapping, nothing fancy. Okay, but it means that it gives you physical access for the frequency. So if you know the sampling rate, then you can draw the frequency response using this real frequency. That's nice. It ties out the system into real world. Which actually, let's see. What kind of filter would you say this 4-point running average filter is? It's a low pass filter, right? So lower frequencies are passed through the system and higher frequencies have some attenuation. But what do you say about this attenuation? It's about 12 dB attenuation on stop band. It's not much of any kind of, it's not really good filter at all. 4-point running average. Actually, the averaging running average filter is not a good filter at all. It's just easy to calculate, but crappy. Don't use it ever again. Not even the suppressor noise. Okay. I have a couple of animations here, just for fun. Let's see. It's animated GIF. Let's see. Does it open? Come on. Do we have a network? Strange. Oh, there it is. Okay. So there I have that special point. Let me turn it like this. It looks better. So the observation point changes from angle 0 to angle corresponding to the fs over 2. And whenever you go into the at the same angle as the 0 is, you get amplitude response goes to 0. There. Okay. Okay, let's see. What do I? Oh, great. So, yeah, that's the same explanation again. Locus maximus on the local minimus at the angle of zeros, and then local maximus on the angles of poles. Let's see a couple of other animations just because I have made them. Okay, that happens when you move the 0 on the unit circle. That's us moving that the place of notch, and this is what happens when you take the pole from the origo and start moving it to the closer to the unit circle, so the Q factor of the filter goes higher because you get more amplification when the system is at the same angle. So basically, doing some tunable filters using this kind of technique would be quite straightforward. So if you have just single frequency and you just define the Q factor and bring the this pole close to the unit circle at the required angle, and then adjust the Q factor by moving it closer or further away from the unit circle. Just a reminder, keep it inside of the unit circle, otherwise it goes unstable. Okay. And let's see the other one. The one waiting. Come on. Network is slow today. Stop playing video games there. You're taking my bandwidth. Yeah, just joking. Well, 15 years ago, seriously, we came up with a problem on networks, but there was an easy fix for that one. The students were really watching porno videos during that was 15 years ago. then they blocked the Oh, bandwidth, yes. Yeah. Yeah, so basically, we about 50 years ago they blocked the pornographic material. That was so wow. And actually, the first what we did on university, we actually had these big computer classrooms. We actually installed some mirrors on the back wall. That helped. That helped a lot. Immediately, nobody was watching any suspicious material anymore. Yeah, and then they started putting also mirror here so that the teacher doesn't do it either. Okay, haha. All right, so in this example, I have actually, it's a Butterworth type of filter. Well, it's modified type. But anyways, it shows why to use these poles. So this is a third order system. It has 3 zeros, 3 poles, which means it's a third order system. And the 0 is marked there just to get a good suppression on the stop band. And then these poles are located so that you can get flat passband response. Okay, so that's basically the principle of how to locate those zeros and poles. So you can adjust the gain of the system with those poles, and it's more cost efficient using these poles than using the same thing with the FIR system, meaning the zeros. You can flatten the passband also with the zeros, but okay, I think we will go through that tomorrow. All right. Phase response. I promised to come back to the phase response. What is importance of phase response? Okay, on analog world, you basically do whatever you can get on the phase response. For the pulse kind of signals, you usually like to use the Bessel function, Bessel's filter, Bessel filter for the almost linearity. But on digital domain, you can make totally linear to the phase response. This requires a little bit of explanation. Just think, well, I will take a photograph just in case. Sometimes I actually post the photographs on the whiteboards. It doesn't take much. So in addition to the crappy video, you can also watch crappy pictures. All right. So phase response, what is so important about it? Think of a signal that goes into a system. Now I have it a sinusoid signal. So you have sine of, I will just mark it as a continuous time. It doesn't make much difference. Mathematically, it goes through the system. What goes out actually is the amplitude response at that angle times sine of omega t plus phase shift at that frequency. Okay, phase shift. If the phase shift is, if that one is 0, then we don't have any time shift either. Shiftless system can be done in digital domain, but this one actually requires, so this is so-called zero phase response. Basically, it requires that you take the signal through the system and then you reverse the time, meaning n equals to minus n. You run the same signal through the same system again, and then you reverse the time back, n equals to minus n, and you have zero phase response. This can be anything, since basically when you make this, you also change the sign on the phase shift, so the phase shift actually cancels out. You got zero phase shift system, which means zero time shift system. And time reverse, unless you own TARDIS, you cannot do it in real life. How many of you has TARDIS? Dr. Who's vehicle? Okay, nobody has TARDIS. I could have rented it just for a couple of days. I would fix my future. So anyway, unless you are Time Lord, you cannot reverse the time in real life, but of course with the computer you can do it. No worries, you have the data on array, you just swap the direction of the array. Easy. And that gives you 0 phase response. Okay. Another important, if this one is linear, phase response, if that is linear, meaning you have some constant C, well, it's K there. Okay. Why it's not? Why it is actually historically K, not C? It doesn't come from English. But yeah, so usually when you have any textbook, there are some constants or whatever they are, A's, B's, and in this formula, it always has been K. It comes from German word, not English word. Okay, but anyway, constant times omega. That would be linear phase response. If we have this kind of system, linear phase response system, then we have that sine of omega t plus theta omega is actually sine of omega t plus k times omega, which is then same as sine of omega times t plus k. That's a constant time shift for any frequency component. Meaning that if you have, say, signal with multiple frequencies, they will be delayed on the system exactly the same time. Think of now the data transfer. You probably want to have all of the frequency components which are coming in to come out simultaneously. Otherwise, you will start skewing the signal. So then the constant time shift is very important for example, data transmission. Or if you are actually filtering data which has pulses. So this, if the phase response is not linear, then the pulse shape is starting to skew. Time delay. Okay. Otherwise, well, non-linear phase response, if it's not linear or zero, then it's non-linear, which means that, well, it can be still used, of course. For example, these IIR systems are always non-linear phase shift, but they are used a lot because they are more efficient to calculate, and most of the applications don't require the linear phase shift. For example, audio. Is the voice, what is that called? Speed on atmosphere, is it constant or not? No, it's not. Different frequencies actually traveling different the speed on air. So you get anyways some, it's called the wavelength dispersion on air in any case for voice, which means that it does not matter if we have some more dispersion on the due to the system. So we can use IIR for audio recording. With some careful design, actually, you can compensate the dispersion. But I cannot think of any use for that. But you can. Definitely, you can. You know, it's engineering. Engineers can do things that people cannot even imagine. Yeah. All right. have absolutely no use for it. But anyways, can do. Um, okay, so that was about the phase response. Directly from phase response, there's a measure of signal delay time, which is just the derivative of phase response, derivative over the frequency. That gives you the time delay. And for linear phase response system, if you derive this k times omega, dk omega divided by d omega would be just constant k. So it's just constant time delay. Okay, some examples of different types of filter systems. If we have input signals as there, it's just a part of square wave. Linear phase response system actually gives you something like something like this, low pass filter, and basically it's symmetric. The output is symmetric, so it means that this overhead before and after the rising edge are the same, so it's totally symmetric. But in nonlinear phase response, it starts skewing this signal, the response, because basically it has this overhead after the pulse edge and never before. Nothing here, but yes, there it is. So if this was this kind of pulse, you can already see that it's kind of tilting towards the end. It's not the same fundamental shape of the input signal. So basically, this linear phase response filter has the fundamental shape of the signal is still there. It's just filtered. Zero phase response. For this example, I actually took this non-linear phase response system and I filtered, started with input signal and used this one as the time reversed that one and used that as the input signal for the same filter, and now time reversed it again, and this is what comes out. So again, it's symmetric, meaning that it preserves the pulse shape. And time delay is 0. See, this exactly happens on the same time, just filtered. But this is not causal anymore, since the event actually happens here, and on this here we already have some non-zero values. So it starts before actually even the input is there. But you know, it's magic. Okay. Then I have some more responses. More or less like analysis tools for signals. You already got this one last week, probably by some other teachers. It's the spectrum analysis part theory. Everything on the spectrum analysis is based on Fourier transforming the signal. And then basically, if you multiply the Fourier transform in the complex conjugate, you got power spectrum. Some actually call it periodogram. Digital signal requires use of discrete Fourier transform, and the FFT is the way to calculate it for historical reasons. And I think already have that one, but anyways. Example of the spectrum analysis, there's a 50 Hz signal at sample rate of 1000 samples per second, and basically if you do the spectrum analysis, you can see this spectrum is not anymore that clean on discrete world because you are cutting the signal with a sharp edge. Okay, spectrogram I showed you yesterday. So it's basically how this answers the question how the signal changes by time, how the signal spectrum changes by time. Okay, good. That was the whole thing on system responses. Impulse response defines if it's FIR or IIR. Transfer function actually is just a Z transform of impulse response. Zeros and poles tell also if it's FIR or IIR. For linear time invariant system, if you have any non-zero poles that are not cancelled by collocating zero, then you have IIR. Step response, just a curiosity actually, mostly curiosity for the digital systems. Arbitrary signal response, basically you calculate on MATLAB, you calculate with the filter. And then the frequency response, it's basically you evaluate the transfer function at unit circle, and that corresponding angle actually there. K, the normalized frequency actually is equivalent to 2 pi f divided by sampling rate, and which gives you the physical meaning for the frequency axis. Zero pole plot, yeah. So those are distances actually, distances of e to j omega to those special points define what is the frequency response. Amplitude response is just the absolute value of frequency response, and phase response, zero phase, linear phase, or nonlinear phase. And group delay is the derivative of the phase response. Spectrum analysis means Fourier analysis. All right. Any questions?